and let me move to share the screen. If there are any questions of clarification as I make my opening comments, please don't hesitate to just unmute yourselves and ask away. As I share my screen, it gets a little trickier to be able to monitor all of your situations, but please just unmute yourself and ask. So in the big picture, we dealt with material properties primarily related to mechanics and strength for analysis and design and support of reinforced soil structures, deformation tolerant through to deformation relatively intolerant reinforced soil structures. The live loads on relatively thin embankments, then more of a dead load or self-weight dominated embankments on soft ground, the sloped structures on competent ground, and then retaining walls on competent ground. We then moved through to take a look at material properties, primarily more related to the hydraulics. I'll revisit just one image from that to support a comment on clogging, but those material properties related to filters and drains, both high conductivity filters and drains, and then we also looked at the relatively low conductivity barrier systems. So that combination of relatively high and relatively low conductivity then has come into play with applications of filters, drainage, and today we get to the barrier systems. And I will indeed make some comments with regard to earth dams and a case history, and the waste containment will fold a little bit into the discussion exercise number 3 that will form our breakout group. So my game plan, the learning objectives for today, let's set those out for lecture number 11. The learning objectives are to examine the nature of the emerging design philosophy. What is it that really underpins the nature of design guidance and the decisions that we take? It's going to be a systems-driven, but systems component design. So let's look at this then as most of the very nice, the thoughtful reflections in some of the better works look at the barrier as a system, and the system comprises components. So although we may consider the components in isolation, it's really the system performance that we're after. And if we have a design philosophy and that's relating to the system components, then let's look at the evolution. And it's not as radical as you might think, ironically. So when I speak to development of design practice over time, this again is where the discussion exercise will come in. To what extent does the work of Stark and Choi, for example, referencing back to the Stark and Popple body of work, to what extent does that influence the way we think, and should it or should it not advance design practice? So those are the learning objectives. They're fairly broad-based, but in the process we'll zoom into rules of thumb and selection of material properties to input into, for example, slope stability analysis. Those are the learning objectives for this particular lecture, a lecture on barrier systems. Okay, now in terms of evolution of design practice, let me turn to BC And what I'm going to argue is there are many similarities and one or two subtle differences between design practice in one jurisdiction versus another. So, for example, in British Columbia, we are guided to some extent by something that started off a number of years ago, actually started off in 1982 as the Waste Management Act. And in 1988, the Waste Management Act acquired special waste regulations. So there was an evolution of, I'd call it philosophical approaches with modest directions. The special waste were regulations. The special waste regulations of the Waste Management Act. In 2004, we can strike out this and move to 2004, and the Waste Management Act became the Environment Management Act. And in the process of that happening, special waste was retermed hazardous waste. So we have an evolution in documents to guide decisions. I've got to tell you that over that nearly 20-year period, nothing really changed in the guidance. And still within British Columbia, maybe I can capture that up here. Even though the dust cover on the book was changing, really the text within the book didn't change at all. And thus we can go in and look at what's expected of an owner and thus the owner's engineer. The owner, for example, of a secure landfill, what's the expectation? Shall design, construct, install, and maintain for this special or hazardous waste a dual liner system. What does a dual liner system look like? A dual liner system looks something like this. There is liner number 1 and liner number 2. Okay, and returning back to the previous page, shall design and construct a dual liner system. And we got a choice of materials. If the liner is going to be constructed of soil, for example, clay or clay-y material, then we have some direction as to how thick it should be. If it's going to be of a synthetic material, then again, a direction on how thick it should be. So we get information on the dual liner for hazardous waste. And if that material is a clay, we have some information, or if it is a synthetic membrane, we have information there as well. What else must the owner's engineer do? Well, we need a leak detection system between the two liners. Okay, we need a leak detection system between the two liners. So there is that leak detection system. Between the two liners. And then finally, the owner and the engineers are directed to have a leachate collection system. And that leachate collection system is above the first liner, because we have leachate coming out of the waste and we want to collect that leachate. Now we might ask ourselves within the system, why might that be, and how is it, what's the intended purpose of that, what's its function, and we'll look at issues of those through the eyes of Kerry Rowe and his ranking lecture. We don't actually know very much about what the leak detection system should be. Just as it's a leak detection system. The leachate collection system is going to be immediately above the upper liner, and it's going to have some properties. It's got a minimum thickness, and although it's got lost in the coloring here and the reproduction, that is 10 to the -3, greater than 10 to the -3. So there we go. There's a philosophy in terms of the objectives and the design philosophy, depending on the nature, depending on how aggressive or how hazardous, and there are criteria for what constitutes hazardous liquid by its biochemical, largely, properties. Then our philosophy is to have a dual liner system and an ability to determine whether or not the primary liner is leaking, and an ability to prevent mounding of leachate on top of the primary liner. And that's largely consistent, excuse me, with US EPA. Okay. We could go to US EPA design guidance, as it's called a double liner system. There is a liner number 1, and let's call this the primary liner, and then a secondary liner. In fact, you know what? Let me add a couple of other observations. It'll be a little easier to do it here, just because this is more open. Let's have this. Let me take this out to the side here. Let's do it like this. Let's take this out over here. And let's take this out over here. And these liners are a barrier. And put in, and it's a barrier. This is a barrier. And that barrier is intended to have a relatively low conductivity. These are the components. Let's view this as the system. Components. Leak collection system, primary liner, leak detection system, second liner. And let's view that what is above here is a drain. And the conductivity of the drain is relatively high. And the leak detection system is a drain, and the conductivity is relatively high. And were we to continue, and it's the last perhaps philosophical point to put in place, we also want to account for the interface strength or friction. So let's view this as system components, and this is hydraulic conductivity. And then let's put beside that interface strength. I'm going to depict the strength as a frictional strength. So let's call that interface friction. And now we could go and look at those. If I call this layer 1, and let's call this layer 3, and let's call this layer 2 and layer 4, then perhaps if we keep things in a reasonably systematic way, we could look at the interface friction, delta 1 to 2, the interface friction, delta 2 to 3, interface friction 3 to 4, and we didn't number it below, but let's call it 4 to 5. Okay. So we have a world that is going to be driven by an interest, and this is partly where the Kettleman Hills experience comes through, the interface friction. And then we have system components where we're interested in the hydraulic conductivity. And the capacity for that hydraulic conductivity or contrasting conductivity to be available over the service life of the structure. And where is the evidence that we're choosing the correct numbers here? Is this too low? Is it too high? Where's the evidence we're choosing the correct initial values to get those contrasts? And then where's the evidence that those values can be maintained or otherwise over the course of the service life of the structure? Okay, and for that, I'm going to spend a little bit of time with Rose Rankin lecture looking at the leachate collection system, or leachate collection and removal. The collection is the primary or the main function, and the removal is a companion function. So that's how I see the philosophy and some of a framework for taking and defending informed decisions where possible. And if we contrast BC with the US EPA, no great difference. If I use the same color coding, here is my layer 1 drain. Here is the layer number 2 barrier. And then a leak detection system, or the term used here, a secondary leachate collection and removal system, but we appreciate what its main function is. There's the drain. And then beneath that, another barrier. So we're going to put that in. So there's a barrier. And then we had a barrier in there. Okay, so we accept that really, if we boil it down, that's the combination. If we put in 2 barriers, we want a dual system for hazardous or special waste. We want to be able to detect any compromise of the first barrier, and we want to drain fluid from ponding and sitting on top of the upper barrier, because that's not really very good for it. It tends to degrade it. That ponding tends to degrade the barrier in ways that we'll examine shortly. And there may be a couple of ways of cutting the manner of the barriers. Here's the geomembrane, and then a so-called composite. FML is a flexible membrane liner, but this is a composite, and then this is not a composite. There's just the compacted clay here, no composite geomembrane. Here's the compacted clay with the composite geomembrane. So we accept there can be a couple of ways of doing this. And then if we move to look at Kettleman Hills, we discover, my goodness me, we can have quite the combination of materials by drain, barrier, and what those individual components of the system are made from in terms of materials. So let's just flag to carry it through. There is that primary liner. There's a barrier. and there's a secondary liner or secondary barrier. So there's a barrier, and there's a barrier, and between them we have drains. There is a drain, and there is a drain. And in terms of interface, oh, maybe one point to make is, and that's along the base. And then if we go up the side slopes, and if you think back to the Alouette Dam spillway, and you remember we moved to geonets on the side wall, the sloped walls underneath the Alouette spillway panels, because the concern was the ease and quality control on placement and compaction of drainage material, under drains in that case, up the sidewall under the concrete panels. And these are essentially under drains. And when we take them up the sidewall, a similar challenge is encountered. So we have a change in materials, right? As we go from the base of the liner, here's the base of the liner over here, onto the side slope, and we necessarily may entertain a substitution of materials. I'm going to use the word variation, but I guess it's in essence a substitution, a variation of, and it's not so much the barrier materials, maybe one of the compacted clays has come out, but a variation of materials, primarily the drain materials. Okay, and that explains why we get these sandwiches. And now that's going to put a challenge on our interface strengths, largely determined as friction here, and that's where things get set out. And I've copied from the Kelvin Hills some of those friction angles, and now we have a choice. Maybe I could even go back here. And ask the question, peak or residual? Okay. And we have information provided to us here on residual friction angles from direct shear and pull-out boxes. Let's look at the direct shear tests, and we have residual friction angles. Okay. And I encountered this myself when I got pulled in to provide just one part of the puzzle on a project. That project was Curzio Dam. Curzio Dam. I'll show you a little bit on this, and then we'll move from the dams to the barrier systems. But Curzio Dam was a dam that BC Hydro acquired. It no longer exists. They decommissioned it. Okay, it was an earth-fill dam, about 685 meters long, acquired by BC Hydro from the city of Revelstoke, who built it in 1963, raised it under their ownership in 1969, and Hydro acquired it in 1972. And in the period before acquiring it, Hydro was aware of some of the challenges. And what were those challenges? Those challenges, and I'm taking information from work reported by a very good colleague, now retired and friend from BC Hydro, Steve Garner, amongst others, who documented the nature of seepage and face leakage and seepage and springs, piping. This is now after acquiring it, 1973. You remember it was acquired in 72. And so hydro now, on the asset they acquired, we're starting to deal with sinkholes and piping and seepage and artesian pressures and more piping, and it becomes a litany of poor performance. And in order to try and address that and mitigate the poor performance, remedial works were undertaken, and those remedial works included, in the early 1990s, installation of a geomembrane. And let me speak to the installation of the geomembrane. Here's an image that I took coming into the site, and here's the geomembrane. It was, there were two patches, one patch here and one patch here. The reservoir has been drawn down to facilitate access, cover material stripped off to expose the core of the dam, and the membrane panels are being placed. Swinging round before landing, and we see here the individual panels, and you may ask yourself, what am I looking at in terms of hydraulic conductivity that I would like here? How might I seam and join to maintain the integrity of that conductivity? And what about interface shear strength? Okay. And if we get down on the ground, and here we see it here, there are the panels as they're delivered, helicoptered in, and then seaming and joining the panels. And here's the nature of the face. This is stripped back cover material here. And there were a number of challenges encountered on it. Sometimes the challenges that you end up spending most time on are not necessarily the ones that you anticipated at the beginning. But the challenge there was to select an appropriate geomembrane. Let me go back. I'm going to use this, even though it's not a hazardous waste. It's a reservoir, but notwithstanding that, so let me put my eraser over the waste, and we have a reservoir, but we still want to choose a material, a barrier that will provide sufficiently low conductivity with no holes or construction defects to speak of. And then we need to know something about the interface shear strength in order to put it in place such that it is stable. So were we to be dealing with the embankment dams, the interface friction and the hydraulic conductivity remain very important to us. The contrast with the waste and the system components in waste is that the biochemical nature of the operating environment may really challenge the manner in which relative values of conductivity contrasts exist. Okay, but philosophically, I guess my argument is there isn't a very significant difference. And on that job at Curzio Dam, then one of our challenges was to choose a geomembrane that was going to be, for example, compatible with the water quality issues. We ended up choosing a fish grade PVC, and then another challenge was the very short construction window and being able to get in and seam and join and get out in the narrow construction window between the snow melt in July and typically full melt in July and early onset of winter snowfall in the September-October period. So a very, very tight construction window. But I'd like to turn at this point to the discussion exercise. Informed by these insights and informed by what we see here, it's quite instructive. I hope you found it instructive to examine the nature of the Kettleman Hills incident. I invite you to describe the nature of the failure and summarize the evidence. Some of the evidence is qualitative, some of the evidence is quantitative, some of the evidence is from eyewitness accounts, and some of the evidence is from forensic analysis. And I ask you to summarize that evidence. And the reason I do that is to get you, let's call it, calibrated to the nature of some of the recommendations that come out of Stark and Choi. Because there's, to some extent, in distinguishing between claims that you find convincing or speculative, it helps to have read about the Kettleman Hills incident before that. So let's turn to this technical note here: peak versus residual interface strengths for landfill liner and cover design. Now that begs the question whether we're looking at basal and side slope liners, or whether we're looking at a cover, or also including a cover going over the top. And they make 4 recommendations. Okay, those 4 recommendations, doubtless you're very familiar with them. They draw upon the Kettleman Hills along the way. But 4 recommendations can be discerned from information presented in this paper. All right, so now let's look at those recommendations. And to do that, and the learning objective here does tie back. Let me return to my learning objectives of philosophy. And now we're going to look at components. We're going to look at the components that relate to interface shear strength. And then developments of design practice with time. How do those developments take place? Do these recommendations, do you take them all at face value? Do they influence your philosophy on residual strengths or combinations thereof? And does that represent, do we believe, a development in design practice with time? So, informed by that, I'm going to stop sharing the screen. And I'm going to send you out in breakout groups. And I'm going to ask you to compare notes amongst yourselves. What do you believe was the rationale for recommendation 1, recommendation 2, 3, 4, etc.? And collectively, do you find them convincing? Are they speculative, or is it some little bit in between? So if there aren't any questions, let me ask if there are any questions of clarification. And if there are, just please unmute yourself and ask away. Otherwise, I'm going to move to breakout rooms. I'm going to create 4 breakout rooms because there are 4. There may be a little logistical challenge to make sure if they're not numbered, I'll have to remember if they are, then who's doing which recommendation. But I'll work with you on that. I'm creating, okay, here we go. So room number 1, which I'll just look at the top name on the list there. Room number 1, first name up is Alex. That's room number 1. That would be recommendation number 1, Alex, and those that find themselves in Alex's company. Room number 2, Daniel, would be recommendation number 2, and whoever finds themselves with Daniel in room 2, recommendation 2. Number 3, room 3, Meredith, recommendation number 3. And then room 4, Grant, and whomsoever finds themselves in the company of Grant, recommendation number 4. And I'm going to open those rooms now, and I'll hold them open for 10 minutes or so. So please go ahead now and join.